Okay, buongiorno. Good morning. Are you ready? So it's not a fake news. He's really here. Come on, are you ready? So I'm really excited because this is probably the biggest crowd we've ever had at our events. And I'm kind of crying because there is no free food. So that's amazing because generally we offer free food. We don't here. So you are really, really keen because you're really interested in having Bjarne here, right? So come on, guys. Thank you. Thank you for coming. So I'm here representing the organization staff, Tiberio Ricchio. Please give him a big round of applause. And Michele Skypejack-Caini over there. And the other folks with the blue shirt you see probably also on the check-in desk, and all the other guys that are helping with this. So thanks a lot. So welcome everybody. Before leaving the stage to our guest and sharing also the stage with the universities that co-organized with this event with us, let me say that I met Bjarne. Oh, this is not working. Okay. I met Bjarne for the first time 10 years ago, exactly 10 years ago in Berlin. So we can say that it took 10 years to have Bjarne here. This is not working properly. Let me check. So yeah, it took 10 years to have Bjarne here. This is true. You can argue. But by the way, we were faster than having reflection into the standard. That was 12 years. So, okay. Okay, I'd like to do a special mention to the ICP, the International Conference on Performance Engineering, who contributed to having Bjarne here on this visit to Italy. So please give them a big round of applause. Thanks a lot. And now I think I can give the stage to the universities who are basically hosting this wonderful conference. So first of all, I would like to introduce Stefano Berretti from the University of Florence, Associate Professor at the University of Florence, and Supervisor on the PhD Smart Computing on Siena, Pisa, and Florence. So,
yes. Good morning, everyone, and welcome to the University of Florence. So just a few words. I'm here on behalf of the Department of Information Engineering, and it is my pleasure to open the door of our university to this remarkable event. Today is really a privilege to have Professor Bjarne Stroustrup here, and if we are here, it's because I think all of us studied on his book. So thank you very much, Professor. And so, as Marco already said, this event has made be possible by the collaboration of our university with the University of Pisa, in particular the Department of Information Engineering and the Italian community of C++. So the result, as you can see, is this open day with the participation of students, researchers, and also professionals in the field. A special thank also to the organizers of the International Conference of Performance Engineering, as Marco already mentioned. And so I don't want to take you more time, so enjoy this morning, and please also contribute actively to the question and answer session later after the break. So enjoy your time this morning. Thank you.
Thanks. Thank you. And now it's time to introduce Associate Professor at the University of Pisa, Tiberio Ricchio, also co-organizer.
Thank you, Marco. So very happy to be here. Good morning. I bring the greetings from the Department of Information Engineering from the University of Pisa here. And you know that we teach C++, but we use C++ as a tool in many of our work at the university, from robotics to system embeddings to high computing environments and so on. So it's something that we really wanted to have here, actually. And when Marco invited us to co-organize this, we didn't have a moment of hesitation, actually, because we felt the opportunity was too great to have here. So we felt to co-organize together with the University of Florence that is hosting us today, and thank you for the opportunity for this here, and with the C++ technical community. It was a great opportunity for that. For our students and PhD researchers that are here, is also a great opportunity, I believe, to meet you, Professor Stroustrup. Sorry for my pronunciation, of course. So I wanted just to thank everybody for this. So thank again for University of Florence for the hospitality. Thank you, Marco, for the persistence also, because I believe for this event we had a lot of patience that probably is worthy of some submission for the standard committee, I believe, in the terms of patience needed for this. So thank you, everybody, to being here. Enjoy the talk.
Thank you again. Thank you again. And I go to the just quick recap of the schedule of today. So we have the talk in a couple of minutes. Then we have a short break. So this break is not really designed for networking. So it's just for stretching your legs or go to the restroom or whatever. So, but moving, you are a lot of people. So moving people is not as cheap as moving a standard vector. So if you can limit, moving around is appreciated, because we would like to be back on time at 12 for the last session. That is the MAA. So this Ask Me Anything session with Professor Stroustrup. And we'll have a slide session. So there is a QR code that I'll show you in a second. You can join the session already. So if you have any questions, just drop them there, and we'll display this later as well. So then we have to go out at 1. So the room is booked until 1 p.m. And we should leave at 1 p.m. Otherwise, the janitors will unleash their fury on us. So if I know that you want to speak with Bjarne. I got email saying, for me, Bjarne is a holy man. I want to touch him, but don't touch him. But that's basically the what I got. That's real. So I know that's real. So you can speak to it. Don't touch him. So you can speak to him. But we have a bit of time later, but please outside of the room, okay? Then more or less, maybe 1:30, we should be, the event should be done, okay? So that's the QR code. So you can join it already if you have. This is open all day until the session, and it works by dropping your questions there and voting other questions. We go through the questions from the most popular ones. So yeah, keep it now, and then I'll show it later. Okay, so I hope you scanned it. Otherwise, I'll show it later. Or just come by later to me. So just a quick announcement. The C++ Day will be again in Pavia this year, October 17. We'll open the call for sessions in a couple of weeks. So if you have any interesting topic to share, please feel free to submit one. The good reason to come to this event is not, unfortunately, having Bjarne there, but we'll have free food in this case. So that's the main reason to come, I know. But, okay, so I think the time has come. So we can kind of have the opportunity now to introduce our guest like, oh, that's not intended, I think. Oh, I got a C++ template Stack Overflow and needs to restart. But we are just collecting error info like the credit card number. Oh my God, I need a C++ expert, I think. You know that? Do you know any in the room? Do you know any? Okay, without any other hesitation. So please give a big round of applause. Join me in welcoming Professor on stage, Professor Bjarne Stroustrup.
Thank you very much. It's a bit overwhelming, but well. So I'm going to talk about generic programming now, and a lot of that is based on the work of Alex Stefanov. That's why his books are there. I actually contributed to the yellow one. Whoops. So basically, Alex had a rather modest aim for generic programming. The most general, most efficient, most flexible representation of concepts. And concepts are ideas in general. So, well, modest is probably not the right word for it. He was very keen on some ground rules. Don't abstract for the sake of abstraction. This is important. I was in France once and I was told never to use the word abstraction because everybody knew abstraction means slow and bloated. No, it is the most precise specification of your solution if you do it right. And you always abstract from something that works. Otherwise, you're just sitting there dreaming up things, and maintain performance as you abstract. So if you abstract from something efficient, the abstraction should be just as efficient. Otherwise, of course, people will use the original, and your work has been wasted. My role in this has been, I want to represent ideas separately in code. Like if you are defining a vector, you want to have the vector here, you want to have the vector type, the element type there, and you want to have the allocation mechanism here, and then you want to merge them together if and only if it makes sense. And then you want to optimize it to the point where it would have been hard to do by hand. And minimize the overhead. And I really want to make generic code as simple as what we think of as ordinary code. And we already have some of that. I mean, you can add two integers, you can add two floating point numbers, you can add a floating point number to an integer. So we already know how to do generic code. Plus is generic, it's always been generic. So we want to generalize that. We have a problem. Maybe I should be up there by the computer.
Have you picked up the subscription?
Maybe I was just too far away from the computer. I'm all till I've seen this work. You can now see I have a reason to be a bit nervous.
We have a backup.
Okay. Let's see. Well, I don't have the magic touch.
I do. I do.
Well,
there is some delay.
yeah, there's some delay.
It's undefined behavior, I think.
No. Oh,
Sort of. There is some
and then
delay.
it did two.
But if you need, I can.
There's an enormous
I can move
delay.
the slides.
I think
I will move the slide for you.
okay. So basically, if you look at Design and Evolution of C++, which was my summary of design aims and decisions about C++ back in '74, I wanted the language to be able to express more than I could imagine. I know very well that my imagination doesn't stretch as far as the imagination of a group of people like this. And we need uncompromising efficiency. I didn't want to have a language underneath C++ to do the hard work. Most languages that claims to be higher call C and C++ to do their dirty work for them. I didn't want such a language. And statically type-safe interfaces, Simula was part of the sort of gene pool of C++, and it was statically type-safe, and that was my aim. Also, if you're statically type-safe, you can run faster than if you are not. And you can find your errors earlier than if you are not. And for the kind of stuff I was interested in, that was very important that you didn't get too many runtime errors. I've got friends who do space probes, and you can't send a repairman to L2 or Mars. So further requirement is that it should be affordable. I started out this as a fairly poor researcher and couldn't use the fancy computers, so it had to work on average computers, and it had to be teachable. The designer of Simula and inventor of object-oriented programming, Chris Nygaard, says if you require PhDs from MIT, we have failed. There's nothing wrong with PhDs from MIT, but there's a shortage of them. And we need to have something that is easier to use. And so this is what I've been working on for a while. And some people ask me, even just now, why are you doing this for so long? The answer is, well, there's some really interesting things that are being built, and I would like to help to do that, and some really interesting, nice people to interact with when you're doing it. So it's the applications that is driving this. Oops. Here. So there's an overview of what I'm going to do. To show a language feature, you have to have an example. And I have disliked narrowing conversions since I first encountered them in C in the 70s. And you really, the idea of having 7.2 assigned to an integer and the 0.2 disappearing is just wrong. And so I wanted to do something about it. And then I'll give the more classical example of algorithms that can be generic. And then after that, I'm going to show that generic programming integrates into C++ as aimed for and as designed. And then I'll show some of the major design choices. And please don't confuse the example for what is an example of. This is not an exercise really in eliminating standard narrowing conversions. I just needed an example to show the power of expressing things that could do even that at maximal checking and minimal runtime checking. So that's it. The basic idea here, even deeper, is when you learn a new natural language, the best way of doing it is to learn to say something. You don't start by learning all of the grammar and all of the dictionary before you start saying something. You start simple phrases, simple uses, and then later you learn the fundamentals. At least that, in my opinion, is a good way of doing it, and I've seen it done badly also, the grammar-based stuff. But this is what I'm trying to do here. Okay, so we start with a problem to drive the design. And basically, narrowing conversions is a source of errors, and I'll show you some errors you may not even have imagined came out of this. And so we can have a big integer and putting it into a little one. Doesn't work too well. It changes its value. You can have unsigned to signed and signed to unsigned and floating point to int and int to floating point. And if you go to the bottom of this list, you'll find one that actually surprised me a couple of years ago. You can have a bfloat, which is the type bfloat 16t. It is a floating point number specifically designed for AI and graphics. It has a very small mantissa. It has a 6-bit mantissa. So if you take even a very small number integer and assign it to a float, you get a narrowing conversion. It doesn't work. So if I don't catch these, you get bugs in things that you might care about. Video games, graphics, if you're AI fans. If you don't catch this kind of problem, you're in trouble. So this is a real problem. And it's a problem that's been standing in C since 74, I believe. And I tried to remove it when I designed C with classes, C++, and I couldn't get away with it. So first, let's define an arithmetic type and then deal with arithmetic types for starters. We can always extend this later, and I will. But first of all, I'm designing a concept. A concept is a constraint on a generic code. So I'm saying that T is a num if it's integral or if it is floating point. And you can actually read up in KNR 1 from 78, and it says so, except it says so in English, and this formal. The compiler can understand it. So basically, a concept is a predicate. It's a function that can be executed at compile time, so that if I get a type foo, then I can say is foo a num, and it'll tell me yes or no. It's that simple. Could I have the next slide, please? So we can look in the standard and see what you can do with arithmetic types, with nums as they are there. And one of the thing I'm interested in is that if I'm taking a T and assign it to a U, can it cause loss of information? In other words, can it mutate what I'm doing, which is almost always a bug. So I'm saying that if you have a T and a U, I can narrow a T to a U. I asked if I can narrow. If it's the same, well, it can't. If they are both nums, I can test more. If they are not, then we're not talking about narrowing. We haven't gone outside that domain. If I give a string to this, this question doesn't make any sense. Can I narrow a string? Well, that's a totally different question. And then if it is a floating point that I'm trying to assign to an integral, then I might miss the fractional part. So obviously it can narrow. Or if the number of digits are not sufficient to hold the result, it can narrow. Or if it's a signed integral and the sizes are wrong, it may change the sign. And that's copied from the standard, where it takes about a page and a half. But I have formalized it. It asks the question, can I narrow a T to a U? Type T, type U. Fine. It's odd notation, but it's something we've lived with for more than 50 years. Okay. It's complicated. It's too complicated. This is why we write code, to deal with it. Now I want to know whether a particular value of type T can be converted to a U. Now we're getting real. So, of course, if it can't narrow, it won't narrow. Therefore, I don't have to do anything more. So at compile time, if I take a short and try and assign it to an int, it'll decide that it has enough digits and it won't narrow. And therefore, there's no further testing needed. Then if it is unsigned being signed to an assigned, then it might be too large a positive number. So we just have to check whether T is larger than the largest signed number. Okay, if it is true, it'll narrow. And if the value is signed and I'm signing to an unsigned, it's better not be negative. So if it is negative, it will narrow. And if not, I just try and assign T to a U and see if I got a wrong answer. Done. So this is the minimal amount of checking needed to see whether a particular value T will suffer the damage when you are assigning it to a U. Okay, oops, it worked. So we can now design a function, convert to, that takes a U and try and turn it into a T. I guess this is bad education because I just changed the meaning of T and U. It's not the right way of doing it. And I was giving a talk on education this Monday. Oh dear. Anyway, this one is testing whether I can convert a U to a T. And it's asked, will it narrow? If it does, I throw an exception. Otherwise, I just cast, because I know it has a value that can be converted. Next, please. So I can test this and I can convert, let's see, what have we got? Assigned integer to an integer, unsigned integer, an integer, This is a simple piece of testing code. And one thing you soon realize is that if people write consistently using convert to, they will never get the problem. However, it's verbose, it's tedious. In real programming, nobody's going to do this consistently. So we have to get the checking, not just being able to check minimally so that the cost is as low as possible, but you also have to make it easy to write. You have to make the testing implicit. Let me try. Oh, okay. So I define a number type. A T is a number, and I store T. And when I initialize or when I assign, I check whether there's a conversion going on. So could I store the U there, whatever it was, as a T? Then it's fine. Otherwise, it'll throw an exception. By the way, the reason I throw exceptions here is that is exactly what exceptions are for. In real code, the problem here, the exception, will be triggered very infrequently, especially after initial testing. We're talking about something that happens maybe once in a billion times, or executions, or something like that. That's what exceptions are for. I don't want to get into error code hell of having to test all the time, complicating my code all the time for something that happens once in a billion. So that's what I'm doing here. And of course, extracting the value is fine because I'm not doing any conversions. Okay, so now I can write code like this. This is better. A number based on unsigned integers, or a number based on characters, and I can write assignments and things like that, and it'll work, and it will throw if necessary. Throwing if chars are 8 bits, throwing if chars are signed and not if they're unsigned and such. This is subtle. This is where bugs come in. I mean, we don't always take care of this. I don't know how many signed integer chars are around, but there used to be a lot. And so we don't think about these problems. So we get problems. This catches it. Okay, so we need arithmetic operators. We're talking about arithmetic types, so of course we have to have arithmetic. And the way to do that is simply to take two numbers and do the operation on them and use the common type. In the standard library, there is a common type for if you have T1 and T2, it looks up to see if there's a common type, which is what you use for operations combining it. It's part of the standard. It's necessary. If you didn't have that, you couldn't do arithmetic. It's been there since, well, since roughly forever, because we needed it. So I'm using it here, even though most people never see it. So basically, I return the number of the common of the result. And this of course, will also do checking if necessary and only if necessary. And so I do that for all the operations, plus, minus, multiply, divide, etc. And one very important thing to remember is to look at less than. This is where a lot of the real world problems happen. I mean, you may not remember that -1 is less than 2 unsigned. I mean, this is absurd. But this is the way the standard says it. It is the way we got it from C. It is the thing I couldn't do anything about. And so we've lived with it for 50 years, even though I dislike it. So mixing signed and unsigned is really a source of problems in real code. I've been looking at code records from big companies and such. This is a real problem, and it's fairly easy to deal with now. You define operator less than for two numbers, and then you see if you are mixing signed and unsigned, and if you are, you do the right thing. In other words, if it's a negative number, it is less than an unsigned number. The negative numbers are usually supposed to be smaller than positive numbers. So that's what this one does, which C couldn't do. So we've done that, and now I can go back and test again. Of course, this is not all of my test cases, but there's one slide per kind of tests. And so I can define auto of some combination, but I can do it better. I can say that the result of an operation like that is a number. And so checking comes in, and I can now write code like x times 2 minus d times z, and get it working and get it checked. There is no narrowing conversions involved in that expression. And that expression shows no signs of generic programming or fancy code or such. And that's how it should be. when you are mixing floating point and integers, you're not actually having to think about clever generic tricks because they're done in the compiler. Here you don't have to think about clever tricks because they're done probably in a library or something like that. And the code looks just like it always did. Okay. Now, I actually came into this by looking at some bugs that was happening, was causing security problems and other really nasty things. And it was observed that a lot of buffer overflow range errors came from mixing signed and unsigned arithmetic and getting narrowing conversions. I mean, this is not sort of fancy type theory. This is practical defense of our code. So here I have an unsigned max. I'm not a fan of unsigned numbers, but this is it. And int a of max, this is fine. And then I want a span. A span is one of my favorite types. It says where things begin and how many elements it points to. That's fine. I was discussing this with Dennis Ritchie many years ago. He called them fat pointers. I called them spans. They're now in the standard. So I say span of A, and I'm giving a size, max minus 500. My finger slipped. I meant to say max minus 50 because that's halfway, but I didn't. Now, if you mix signed and unsigned arithmetic in C and C++, you first convert the signed number to unsigned, and then you carry on. And so that 500 got converted. What happened here? Can I see the previous one again? Yeah. There's something there. So the minus 500 is converted to a positive number, and it's very large, which means that any checking you proceed to do in span will not do any good because you're testing against a low number, and it says that everything is available. That's how you get really serious bugs in real serious code. Okay, but we can deal with that. I should just point out that until I started tackling this problem, I wrote 42 lines of code plus the arithmetic operators to get everything done this far. This is not rocket science. It fits on one screen. Okay? If it looks odd, if it's new to you, you can do it. It's one page of stuff. And I have a paper describing it. So anyway, we're going further. Let's fix the problem here for spans. And so I define a concept spannable. There actually is one in the standard library, a concept called ranges : contiguous range. It asks whether things are a contiguous range so that you can subscript into it. It just got a bit long for me, and also I want to add to that concept. So I start out by naming it. Could I have the next one? So I can define a span, and you initialized with something spannable. So span, spannable, auto, ref of S. Auto is redundant, but the standards committee wanted it. Basically, you can make a span out of anything that's spannable. Makes sense, right? You can have a span beginning to the end as long as there's a contiguous sequence of elements. And I can check whether things are in range with a check there. That's fairly simple. And I can return a subscript into it. Again, with number, it hasn't wrapped around. So it's fine, we check. Next, please. So I test it, and I try to cheat it with -10, it's not a good index into a span, so it will throw. I try a span of a different type, and I keep on making test cases. The interesting one down is the bottom there, span out of a value taken out of another span. In other words, I'm doing what people are doing all the time with subscripting. They're taking a subscript from some computation and using it to subscript into some other container or range, and they get it wrong ever so often because the computation didn't do what they thought they did. Now here, it will test if and only if a test is necessary, and it will catch any range error. And I didn't have to write any special code to have it tested. It's all done by the number library, which, as I pointed out to you, fits on roughly a page. This is a bit verbose, and we can shorten it using what's known as class template type deduction, usually abbreviated to CTAD to confuse people. The standard committee likes experts and they like fancy words, but basically I'm going to deduce that if what is the element type of a spannable? It is, of course, the element type of the span, of whatever it was that was spannable. So there's a notation for that. It just preserves the element type. And oops, no, not yet. So I now take an array of 100. What do I take? 100 of integers, and then I say I want a span of that. And the compiler already knows that it's a span of integers, so I don't have to say that again. And it actually also knows that there's 100 of them. That was a constant, so I don't have to say anymore. And I can now start doing things like range for loops and algorithms and other good stuff like that, that knows there's a sequence, it knows how many elements there are and such. Okay, so I can now do that. And that's nice. And again, you saw the code, all of it. So it's real. Can I have the next one? It's not good enough, though. This is oversimplifying. People always want sub-ranges, and they also, unfortunately, need to get a span of a pointer they get from somewhere else, from your graphic system, from your operating system, from some weird allocator or something. And then you have to say how many elements there are, because it's not known. I mean, it just came out of the operating system. I have to know the sources, how many elements it pointed to. So I add some more constructors to span. One that takes a pointer and then a number of that's unsigned, so I can grab these weird pointers and elements that comes out of somewhere else, and then I can take a span, which take a subspan, the first n element, and the spannable there takes a low and a high. And the code is there. It's using the fact that everything that's spannable has data, everything that's spannable has a size, so it's easy enough to deal with. The thing that's the trouble is the pointer, comma, number of elements. That one can't be checked automatically. Not that it's difficult, it's impossible in many cases. So we need it. Next slide. So again, I write the type deductions that says that the span of something is something that's pointed to by whatever you give it. Fine, that's funny syntax, but you just write it once and it's done. Next. And now I can write things like that. I have my integer array again. I span it to the whole thing. I span it to half of it. I try and span it to twice as many elements as it's got, and it will throw. You can't do that. It's testing it properly. So that S3 will not pass. And I can try the first 20 elements, and if SV, if V, V I got it, so I don't know it's R, but this is being implicitly tested. So you can't make a range error out of the SV1, SV2. And finally, I do some more stuff, including taking the pointer I just got in as an argument and trying to take a span from the beginning of that pointer to 10 elements. And that cannot be tested. Therefore, it will stand out like a sore thumb to a code review or to a static checker. I want a static checker that flags that SP down there for review. That's the best we can do. If you want to close that hole, you can no longer deal directly with the operating system or with hardware. And in other words, you're not C++ anymore. And you would have to call something like C++ to deal with it. We deal with it here and we flag it as known to be dangerous. Okay, so more type deduction. Now number is beginning to look rather verbose. I have to say number of a type. What kind of number is it? But I can deduce what the number type is from its initializer. If I have a number that's initialized with 1, it's a number of an integer. Of unsigned, it's a number of unsigned. A floating point number, that's a double, it's a number of a double. I can now simplify that. Now I only need to say the basic type of the number if it is different from the initializer we're using. So if I want to have a number of doubles initialized with an integer, well, I better say I want a double, otherwise I'll get an integer. So that's sort of the first part. This was what inspired this particular talk, and I just attacked a real problem. Whether we can ever get that, you can write a library and use it. The reason that I haven't finished it is I really want to combine this with something that checks for overflow of integers and things and underflow. And so I feel it's not quite finished yet. But if you just want to get rid of narrowing conversions, well, there's about 120 lines of code that'll do it. So now I'm going to go to a more classical example, the kind of example that people always do for generic programming. And here's a sort, the way Alex designed it. It's a photo of Alex Stefanov a few years ago. So basically, you take an iterator for the beginning, an iterator, and that way you can express all kinds of things. And the standard says exactly what properties are for a random iterator. It's a pointer-like type that you can use to iterate over a range of elements. It must provide random access to that range. And the element pointed to by the random access iterator must be comparable with a less than operator, or you must define your own comparison. And this is good. Let me see the next one. It's very good, spectacularly successful. It's efficient, it's flexible. It has appalling error messages because you just said what should be the case. You didn't tell the compiler, and you can do all kinds of good stuff. I know many of you will have been doing it, and many of you will have been suffering from the error messages. The problem is this one does not fulfill the third criteria on my list of things that had to be done. It doesn't specify precisely what the interfaces to the sort is. It just says it has to be a random access iterator, and you can look up in the manual, in the standard, what random access iterator is. And by and large, we don't do that very often, and the compiler never does it. So the compiler only finds out there's a problem when you're doing an operation that wasn't provided at instantiation time, at link time. This is awful. And it also violates the design criteria for C++. So let's deal with it. So basically, we have to tell the compiler that we need a random access iterator, that's what you want. And you want that random access iterator to be sortable with the predicate that you are giving it. And so we just tell the compiler what we knew and what the standard knew, but the compiler didn't. And therefore we got the bad error messages and the late error messages. So here we just have to define what random access data is. In other words, we need a concept. In other words, we need a compile time function that you can point at a type and says, are you a random access iterator? And it requires sortable because there has to be a relation between the iterator and the comparison operator. Obviously, the comparison operator has to work on whatever the iterator points to. We have to say that in code, so we must. But basically, this becomes easy because it's mostly in the standard already. The standard I'm talking about here is C++ 20 and everything later. And so I default the predicate to less, which is what we use the most, and we just add a predicate if we feel we need to. And so now we can write the same code as we always did, but we only got better checking there, and we can do things in descending order, ascending order. Let's see, I'm trying to sort a list there. And the difference here is that it asks whether the list has the properties required to be a random access iterator. And the answer is no, it does not provide subscripting or going in elements over. So right there at the last line, we're going to get an error message. And if you do it right, the error message is really what it says in the comment there. I had an experimental version 8 years ago that did exactly that. Currently, they're a bit slow in upgrading the error messages, but at least you get it in the right place. Next. And it also addresses some, no, we need to address some other problems. The examples here have been seen in the wild. Vector end, comma, vector begin. Somebody cut and pasted or typed back. Sort for the one container's begin and another container's end. This is not going to be, this is not common, but it's been seen in the wild. So the problem is we haven't been precise. One of the things that we want to do with C++ is precisely say what we want and have the compiler check it. And you know, most of the time, I don't actually want to change to sort from the beginning to the end. I want to sort the vector or the span or something like that. And I have disliked that amount of typing since I first saw it, but I didn't see any alternative. Overloading on traditional unconstrained template arguments is very hard. So basically what I want is a sort vec. If I do that, I can't flip beginning and end. And if I sort S1, I cannot get the end of V2. So let's go and sort things there. So I define sortable range as a range that you can sort with iterators. That's again a concept, a constraint, a predicate, a compile time function. Your sortable range, if you are random access range and your iterators allows you to sort with your predicates. My guess is you are now beginning to be able to read this. Okay, next please. And now we can use it. We define sort as sorting a range with a predicate. And I implemented the easiest way I could find, which was I simply used the old sort. I mean, you might be able to find cleverer things, but this one was easy and fast. And your average compiler will actually inline so that there was zero overhead. And now I can sort the vector and of doubles, vector of strings, sort ascending, sort descending. Everything is fine. And I no longer have to type so much, which is good because I'm not a good typist. And when I have to type a lot, I can make mistakes. So this is much better. It's less error prone and easier to write. Next. So I sometimes ask, what if we wanted to list? Why can't you sort lists? Well, you can sort a list if you really want to. The list type has a sort operation, but lists are really lousy for sorting. It's a very bad data structure for sorting. You have, instead of going over there, random access, you have to go over there. And if over there is 10,000 elements over, even modern computers will slow down. But say you wanted to do it, we can do it. So here I define a forward sortable range. It's not in the standard, but it's basically a forward range that you can sort with the iterator it has. Fine. And then I can define the sort function that takes a forward sortable range. And I implemented it the simplest way I know. The elements over in a vector, sort it and copy the elements back again. Surprisingly, this is good enough almost all of the time. You should only tune things if you need to tune them. There is an algorithm that's supposedly better than this, at least for larger elements, larger containers, but I've not had to use it. Next. And now, here comes the important thing. We can overload based on concepts. So here I have a vector and I have a list. And I say, sort the list. And it will look at the sorting of random access and the sorting of forward. List isn't a random access, so it doesn't pick that. So we've picked the right one already. And we try and do sort of vector. Vector can do both. And the rule is that if the constraints on one algorithm is a subset of the constraints on the other algorithm, we can pick the one that is most constrained, because that's the one that has more facilities for doing a good implement, things like that. So we pick the vector here. We don't have to build hierarchies. We don't have to build relationship between types into the types. We don't have to have special names for all the algorithms and things like that. It's just resolved naturally. I like that. This is overloading, but the overloading rules are far, far simpler than the overloading rules for basic C++, because I don't have to deal with the old distinction between built-in and user-defined type and things like that. It is simply, if nothing matches, well, it's an error. If only one algorithm matches, it's that one. If two algorithms matches, if one is a subset of the other, we pick the most stringent, otherwise it's an ambiguity. End of rules for overloading. So let's look into the design of concepts, because now we're going from everything we've done now has been to do with use. How can you use concepts? And I've told you what a concept is. It's just a function. You've all known functions for a long time. But let's see what it really is there. We've always had it. C had arithmetic and floating point, even in 72 or so. The STL has iterators, sequences, and containers, but they're only in the documentation. Math has lots and lots of concepts. I picked monad, group, ring, field, and such. But basically, every field we have is full of fundamental concepts. The graph has edge, vertex, graph, and dark. It's had them since 1736. We know exactly when. This is the Bridges of Königsberg paper. And but anyway, we didn't invent the notion of concepts. I didn't, Alex didn't. It was there floating around. We just had to formalize it. Alex worked hard on getting algorithms specified in terms of concepts. I worked hard on getting his stuff to actually work and run fast enough. He tried in Lisp and Ada and failed, so it's a non-trivial operation. But anyway, we can do it. And no generic programming would ever work unless the concept was in the head of the writer, at least, and possibly in documentation, but I'm not a great fan of documentation because I've seen too much of it being wrong. So if I can get it for the compiler to be checked, I'll do that. So that's what we're doing next. And so concepts tend to be built out of other concepts, just like functions tend to be built out of other functions. So basically here, it's the example we saw before, a forward sortable range is a forward range that can be sorted. Just like we write other functions, except this one takes types as arguments. That's fine. Compiler knows about types. So soon we will too, probably. And we just write it. Sometimes we have to go to the language itself. Can I get the next? Where we actually have to express a concept out of fundamental rules of the language, just like sometimes we have to write a function in terms of the for loops and if statements and such. The way I see it is, if you write a square root function, you have to deal with the language and you have to know a lot of things about the language. Most of the times we don't. When was the last time you wrote a square root function? In my case, we go back to the 70s, because I know that people who knows more about floating point manipulation wrote the square root function, so I just use it. So the previous slide was done the way we actually do it for real with normal functions. This is when we have to drop to the level of the implementation using the raw language. And we have a requires clause. It says if you have a t called A and a u called B, and we want to compare them with equality, we test A equals B, yield a Boolean. Boolean is a concept. It's anything that can be used as a Boolean. Usually it's a bool, but there's a lot of old code out there that uses integers and other stuff. It still works. And so I can also do not equals. I really don't want something that only works one way and not the other, equals and not equals. And I want the operation to be symmetric. B equals A in equivalent to A equal B. So it more complicated when you drop to the standard level, but this is how you do it. You use the requires clause, and you can, of course, express a combination of requires clauses and other concepts and all of that kind of stuff. It works. Next. So one thing we use is use patterns. Requires, say I want to say I requires A plus B, which is a fairly standard thing. The problem is that in C++, people can and do define things like plus in a variety of ways. You can have it as a freestanding function, you can have it as a member function, you can have it as a class hierarchy, you can have it where you deal with implicit conversions to get to the type what you're talking about. So you must be able to do A plus B instead of saying exactly how you must do it. You get the code simpler and more stable. The reason this is mentioned is that a lot of designs of constraints are expressed in constraints in terms of a set of functions with specific types. And so it would only work for one of these alternatives. So the use of use patterns here gives flexibility and simplicity of expression and leaves a little bit of the work for the compiler. The compilers have known this for decades already, so that's not a problem. And this is important. Concepts handle mixed mode arithmetic, it handles implicit conversions, and it handles concepts involving many types. So this is much more flexible than a lot of more theoretical solutions to this problem. Next. So the checking is implicit. And you don't have to write anything to get things like that plus or that equals or the sortable concepts done. But you can if you want to. So you just take a static assert and says int and doubles equality comparable. Yeah, they succeed. We can argue about doubles, whether they should and such, but they do in C and C++. And I defaulted the second type to the first type, so I can ask, are ints equality comparable? Which they are. And I can assert that int and strings are not equality comparable. And again, this is checked at compile time. So if you want checking, you can get it. And if you don't want checking, just don't. That means that the set of types that will work with a set of concepts, with a set of algorithms, with a set of functions like that is open. But if you want to do early checking of some of the cases that you know of, you can do it. Next. So I sometimes hear that generic programming wasn't meant to be in C++, or it's not natural or an accident. I hear a lot about that. It's not true. So I'm going to talk a little bit about why generic programming with concepts is an integral part of C++ and has always been the aim. It's not a sub-language isolated from the rest. It works together with object-oriented programming, with normal functional, with normal procedural programming, functional programming and such. Looking into this, I noticed that I had done something back in '79 that was absolutely essential. The rules of how the syntax rules and rules for initialization and such for user-defined types and built-in types are identical. The rules for what you can point to with pointers are identical. And the rules for resource handles, creation, deletion, are identical to the ones that aren't resource handles. So This is not the case in Simula, it's not the case in Java and things like that. But this is essential for generic programming, because generic programming says that there are certain operations you can use for all the types you want to. And if I couldn't do what I did there in the beginning, I would have to have two algorithms, one for built-in types, one for user-defined types, actually a third one for resource handles. This all works into the same thing. No, not yet. I'm sorry, I have some more talk to do. Lambdas work, generic or not generic, and you can generate functions. I'm going to show about optional member functions and modules and static reflection to show how it integrates. But basically, the ideal is that generic programming is just programming. And I can credit Dennis Ritchie for starting this with integers and floating point numbers. It's old as the mountains. That's a picture from the Space Telescope, by the way. I like applications. Next. So yes, this was what I said about uniform treatment of types. I don't have to say it again. Still. Next, please. Yes, optional member functions. One thing that we find when we're writing foundational types is that types should have operations only under some conditions. Is there one before this? No, next. Okay, there should be one before that. That I wanted, example, where a smart point would have an arrow operator if and only if it has, if it points to a class. And the way you do that is you define operator arrow requires the element type being a class. That's the simplest version of an optional member function. You only got the arrow operator if you are a pointer to a class object. Now, here is a more difficult and interesting example, but I shouldn't have skipped the simple one. Here I have a pair type. And the pair type, you should be able to construct a pair from another pair, provided you can convert the first element into the first element, the first element into the first element. And that's what I've said there. And that's fairly simple. Now, this pair type of T and U, you can assign maybe I've done this backwards, but basically the idea is you simply says that if you can convert the two elements and the source into the two elements of the target, things work. And then this I can write in standard. And then I noticed that this does not check for narrowing conversions. So in terms of this talk and in terms of my library, this is all wrong. This is what the standard says, by the way. And it's much more complicated to do. You don't have concepts. Anyway, let's go to the next one and solve this problem. I can do much better. I can convert a TT, U pair into a T, U, provided I can convert the T value into the PPT into T and the U into U. It goes and does all the testing we did about an hour ago, and it just works. And then I noticed that I had done a simplification earlier on that I probably should have. It doesn't work for pairs that are not arithmetic types. But now we have overloading. So we just overload convert to work for things that aren't arithmetic. Overloading will make sure that if it's arithmetic, it'll use the arithmetic version. But if it's a string, it's not an arithmetic version, then it'll just use the version you see there, and it'll just try and do it. And well, so we've added that with overloading, and now it works for a pair of int and strings and things like that. Next. So this also works with modules. It should. I mean, I worked on modules for a long time. If you look into design and evolution of C++, you'll see that I wanted an import statement, and we've got it, and they work very fast. There's a lot of talks about them, so I'm not going to go into it here, but if you haven't experimented with modules, you should try it. I usually use import std, and it runs 5-10 times faster than just an include of the libraries. But anyway, here it works. I'm exporting a map printer, I'm importing a lot of stuff, and I'm exporting only the map function, and I'm using a concept here, namely sequence. That was what I wanted. So it's integrated with language is a point here. It is not a facility that's sitting over here and is separate for other parts. Next. And now we'll get to reflection. Somebody mentioned reflection before. You actually underestimated how long people have been looking at it. David van der Voorde has been trying to do it for at least 20 years, and I've been trying to support him, and we've gotten absolutely no way till recently. And by the way, static reflection, again, works with a bunch of compile time functions. So you go back, and when Gabriel Strays and I got constexpr into C++11, we knew we were opening it's a camel's nose, right? I mean, you get the camel's nose into the tent, soon you have the camel. Constexpr was the camel's nose. And now we have concepts, we have static reflection. There's people who want to do everything at compile time. That's a dumb idea. You actually have to think about what is worth doing. But I'll show you something that is always done at compile time. So let's take a simple example. I want to generate a descriptor for a class. That is something I've needed in many application areas. I have a class. I want a layout of that class. What are the elements' names? What are the elements' types? What are the elements' beginning location? What are the elements' size? I think I didn't store the type here, but I could have. This is because it has to fit on the slide. But basically, I want to generate data member descriptors, name, offset, and size. Fine, they're useful. And the code for doing that looks like this. So we have a function, non-static data members, and it is applied to a reflection, a meta piece of information. Basically, when you say hat of a type S, you gain access to everything the compiler knows about X. And then there's a bunch of functions that can use that, like if I have a class S and I want the non-static data members, the type system will make sure that it is something that has data members, and then it'll give me the data members. And then I can go through and saying, I want an array of member descriptors. Those were the ones I wanted. And I want as many elements in that array as there are elements in the type. Fine. So that is member descriptor, comma, members size. Because members was when we got the information about that the compiler knew about the function S. And basically, of course, what is happening there is that nothing much is happening. It's just we're gaining access to this stuff inside the compiler there. And then I'm saying for each of the elements, the layout is the identifier of the member I, the offset is the offset of the member I, and the size of is the size of the member I. And this is all in the standard. The data structure that you are given when you do hat has a set of perfectly ordinary functions that extract information from it. Fine. And now I'm finished. I can return the layout. And let's try and use it. Next one. So here I pick again, this is slideware, a very small standard simple data structure. I have X that has a char and int and a string, and then I'm just saying, give me the layout of it. And now XD there, the layout, is an array. It has data member descriptors, and they actually have the value A, 0, 1, B, 4, 4, and C, 8, 24. And the reason I use funny quotes there is that these are really string views. We're not actually copying anything. The compiler holds the names somewhere, and I'm just getting a string view to the stuff that are inside the compiler. So this is not only reflection, it's also dirt cheap reflection with minimal copying, minimal new data and such. Because what I don't like about runtime reflection is that it bloats my data space, and it forces me to do a lot of untyped graph manipulation. This stuff just, once you've written the previous function using the hat, it's a perfectly ordinary function, and it's optimized in the perfectly usual ways. Okay, next. So the major design decisions for doing this was basically that the concepts of functions, the concepts can be partial, and I'm going to show that next. Concepts of functions for flexibility and generality. There's few things that are as flexible and general as a function. And the functions can be done at compile time, and the functions we're talking about here can take type arguments. This is flexibility and performance beyond what we usually have. It relies on the use patterns so that we don't have to know all the details about how the operations are implemented. And you can have multiple arguments. I find that about half of my concepts take more than one argument. And the logical reason for that is that if you have a function, a generic function, that takes two arguments, either they're the same type or they're different. If they're different, they have to have a relation to each other. If they have a relation to each other, we have to express the concept as this one has to match that one. This is what a lot of type systems simply can't do because they think properties are part of a single type. And we needed that to do mixed mode arithmetic and implicit conversions. There was an attempt to do concepts for C++ OX, what became C++11 because we were a bit slow. Actually, we were very slow. And that didn't work. And the place where it really broke down was, well, we couldn't get the type safety right. We couldn't get the mixed mode arithmetic right. And those, it just didn't work. This worked much better. And concept can have multiple arguments. And by the way, concept can take value arguments just like templates. So I could define a concept of a buffer that takes at least 1K elements. I think I have an example. Yeah, I have that example. So I have the concept of a buffer space. There has to be at least 1K elements, and the size has to be a power of 2. So I can define that concept, and I can say my buffer type to have element T and size S, and it requires that S is a value that is allowed for buffers. And now I can say buffer char of 100, the buffer is too small. Buffer of int and 10,000, well, I said I wanted binary powers for my size. That is not it, so it's not right. But an int of 2K is all right. So I can do that kind of checking too. Next slide. And in case you don't know how to calculate a binary power, there's the classical way of it. And I've done const_eval, which is a function that has to be evaluated at compile time. I could have done const_expr too, but I... next. Again, that shows how things integrate from one corner to another. I had a lot of debates with people whether programming was object-oriented programming. It isn't. And whether object-oriented programming was better than generic programming, or generic programming was better than object-oriented programming. And my view is that they're complementary. They have different strengths. And there's a list of things there, but basic classical object-oriented programming focuses on types of objects in class hierarchies. It applies to one concept at a time. If you look at generic programming, it focuses on requirements on algorithms, and it usually, at least half of the time in my experience, involves more than one argument. So that's different. On the other hand, object-oriented programming specifies precise interfaces to functions and such, so you can have it runtime resolved, whereas everything to do with generic programming has to be compile time resolved. You can only work on types that you actually know, not types that is defined tomorrow in a class hierarchy. And so I think they are complementary. As I said, read the paper that I wrote about it. There's a couple of pages explaining this. I don't like going through long lists of comparisons. That's not what talks are for, in my opinion. Next. And so they're complementary. And here's one of my favorite examples, which I first got from Christian Nygaard, who invented object-oriented programming. It's the draw all shape example. But here I'm doing it in modern C++. I want to draw all from any drawable range. So it has to work for any drawable for which the elements can be drawn. That's what I want. And the code there is a range for loop that goes through all the elements and draw each of them using the arrow draw function. And I can define the drawable range. As I said, it requires that you can draw, and it has to be a range. So that's what's defined there. And so for people who are interested in paradigms, what paradigm is this? Is it object-oriented Of course it's object-oriented. It's a classical object-oriented example using virtual functions, maybe. It's also generic. There's full of generic stuff. And actually this works for cases that the object-oriented programming don't work with, because if I can define classes with arrow operators that are not in a hierarchy. It'll still work here. On the other hand, it works for class hierarchies, so I can define class hierarchies, so I can add classes at runtime, basically, things that wasn't known. So this example can do things that object-oriented programming can't do, and it can do things what generic programming can't do. So much for paradigms, actually. That these things are complementary. You can use both. Next. Partial constraints. I thought, like many people, that to define a concept, define a set of constraints on functions, I had to be complete. And I very soon realized that not only is it hard to be complete, but sometimes you're not. When you're building a program, you only know part of the constraints needed for. Here I have a number, not the number we had up before, which was precisely defined, but this one says, well, if you have plus, minus, multiply, divide, etc., I'll treat it as a number. And it will catch most things that aren't numbers. It will not actually check completeness because it hasn't said anything about copying and assignment and equality and such. But it'll help me while I'm debugging. It'll help me while I'm defining the concept. It'll help me while I'm using the concepts. And I found this was extremely useful. So partial constraints are useful. Next. Let's see. Then people said, well, if you are looking for properties, you can get false matches. And I'm saying, well, the false match of a type, a number, something that's not a number and has all of these properties are extremely unlikely. But there are cases that happens. Next. We have a concept of a forward iterator, and we have a concept of an input iterator. And they're very well defined. They've been used for decades, and they're actually more or less necessary. The only difference between a forward iterator and an input iterator is that you can repeatedly read a forward iterator, which is useful for some algorithms. Repeatedly read an input iterator, you don't get the same answer the second time you read, so they're different. And there's a simple solution by the fact that these two are identical and you'll get ambiguities all the time. That's good. If you haven't defined them properly, then you'll get. And we them very simple. We give one of them a property, the other one don't. Yeah, maybe this one works better. It could be the battery. I will try and do it more. I'm not a fan of these things. I feel I should sing, and you would pay me extra for not singing. So you can always add a property. I traditionally added a function saying can repeat. Here the standard says that there must be a forward iterator tag, and the input iterator mustn't have it. So you just add another feature. So if they're only semantically different, add a syntactic difference and the problem goes away. Next. Then, like everybody else, I thought a very important part of constraints was that you would be able to compile generic functions in isolation. And we found that was one hard to something people didn't want. Here's an advanced version, a function, the standard function in the standard library, slightly simplified. But I have just done something. I've added some infrastructure. I want to log that this one has been called. And especially in industrial software, not so much in academic software, you have all kinds of infrastructure. Logging, debug help, telemetry, statistics gathering and things like that. And so you have a choice. You can either allow that stuff without checking that it is available, or you can change the interface to advance to have log in it. I've done functional programming where I had to change the interface, and that gave instability that I didn't like. So people wanted to be able to do their logging, and it's even more fundamental. Notice I required an input iterator, but I used plus equals. A plain old input iterator doesn't work with just with plus equals. But this still works. I think the next slide will show what we have been doing for 20 years since Alex's version of the STL came in. You have a vector and you want to advance its iterator. The compiler knows that vector has a plus equals, so it doesn't catch it as an error. It just knows that whatever we feed that advance can't just be an input iterator. So it works. And the difference is that the performance of some algorithms differ from ON to ON squared if you couldn't do that optimization. So we concluded that we didn't actually want separate compilation of templates. And there are people who express it slightly stronger. They will not accept any facility for concepts that requires that checking. And so we're not going to get separate compilation of all templates. And if we get any, it'll be because I figure out how to distinguish the ones where I want to have this flexibility and the ones I don't. And I'm not optimistic that I can do that. Next. So basically, this is the end. Generic programming is just programming, and we're getting close to Alex's ideal of the most general, most efficient, most flexible representation of concepts. But remember, it's complementary to object-oriented programming, so it actually does even more than what Alex wanted. And it's based on classical math. It's just functions. And it treats built-in user-defined types uniformly and complementary to OO. And the concepts, compile time functions, can take multiple type and value arguments, and specifying what a generic function requires from its arguments, and can be used for overloading to select among alternatives. And basically, one way of seeing this is we can build our own type system on top of what C++ gives us. So the numbers I designed up front are exactly the same as the built-in types of C and C++, except that they can't narrow. So I built another type system on top of C++. And it's also provably optimal if you need the runtime checks, and because I pushed everything that could be pushed into compile time. I think we should take a few questions now about this talk only, and the AMA that is freewheeling goes after the break.
Great. I think we can. Doesn't work. Okay. I think we can spend something like 5 minutes for these questions. So if you have any, please raise your hand. We'll try to reach you.
Hi. I have just a question based on my experience. So I moved from building software, well, to review it, so to review the code and so on. And how would we improve our reviews given the extra complexity that all this adds? Of course, I'm talking about cases where developers don't use these to do just the basic underground of the code, but rather use that actively while they're coding. So getting, template explosions, class explosions, and reviewing all of them, at least for me, was very painful. So do you have any suggestions?
Yes, that's basically a different talk, but this talk was how to get generic code, and I was using the generic code to simplify code. If people really love writing old-style code in complicated ways, this will not help them. However, I'm working on something called profiles, which are basically formalized coding guidelines that are checked. So look out for profiles. We didn't get them in C++ 26, but the idea is you extend the language with something like my number type, and then you at the second part of it you subset that superset, taking away the direct use of the built-in types. And now you have only the improved version. And we're doing that with things like initialized and non-initialized, and with hardened standard libraries, but taking away the subscripting of ordinary pointers and things like that. Educators also like that idea. It's not just safety, it's simplifying the language. But that's another talk. Actually starting to work on it, but it's not there yet.
It would be a lovely feature, by the way. Thank you.
Hey, it's a pleasure to have you here. Actually, 2 questions. I would like to understand, recently I've been reading the Liskow's paper on the behavior subtyping, and I see that the concepts programming is heavily influenced by Stepanov. I would like to understand if also her concept of subtyping is also indirectly influencing the concepts programming in general, in generic programming. And the other question is about neobloid patterns, and what was your first impression when, for example, Nebler could circumvent argument-dependent lookup?
Okay, I think neobloids is a big mistake.
Yeah?
That's as simple as that. I didn't notice them too late. I trusted that people would do something sensible, and in my opinion, they didn't. For the first one, I didn't quite understand your first question. Could you repeat?
Yeah, basically, there's Barbara Zliskov's paper on behavior subtyping.
Which paper? That's what I mean.
The name of the paper is behavior subtyping, and the concepts of behavior subtyping. And basically, it's mapped to what people know as Barbara Zliskov substitution principle.
Yeah.
And to me personally, it maps much more to generic programming than the classical OOP view. And I would like to understand if that's your impression, if you are familiar with the paper.
I am not familiar with the paper. I'm familiar with the Liskov substitution principle. I was there when she presented it. I was very shocked because I'd already built into C some years before, and she had just. So yeah, I mean, you should be able to substitute if it's a subtype, if it's a here it's a subconcept. In object-oriented programming, it's a public base class. If it's a private base class, it's different. Similarly, if there's no subset property, it's different. But I can't say anything about that paper because I may very well not have read it.
Okay, thank you.
I think we have time for one last question. Okay.
Thanks.
There's always the AMA.
So I have just one question regarding concepts and the relation with the common software pattern of using virtual interfaces classes, I mean. So would you foresee in the future that software developers will start using more of a concept first approach to defining type constraints and type contracts? Or would you keep seeing them as egalitarian approaches? So whether I should use virtual interfaces or whether I should use concept does not make any difference.
I would like to see people using concepts first, and then having types that matches the concepts. But to build a good concept, you need a first type or such to get started with. So it's not just a one-way thing, but I think concepts first. And I don't think people need to know whether something is a class or not. It's just if it meets the constraints, it's good enough. People who want to have ABIs will have more constraints than what I am saying, but they can express them.
Okay, you can join anytime at the QR code and vote all the questions. So the first question is from Dimitri. Where is Dimitri? I'm here. Okay. So I think you can read it, but yeah. If you had the ability to do so, which language constructor feature would you revert that is removed from the standard and never have introduced in the first place? And what would be the main reasoning behind that choice?
Now we'll see if this microphone works better.
Yeah, we are trying five different microphones.
Can you? Yeah, you can hear me now. So, sort of the generic answer to this before I go into specifics. I think the major parts of C++ I chose correctly. And every major part I could do better in retrospect. So if we then focus on the major things, I really want to get rid of the preprocessor, and we could do it now. It'll have to take some time to get rid of it, but getting rid of includes and macros and if NDEFs and such, you can do without it today. And if I had to design a language from scratch, it wouldn't have those. Secondly, of course, the narrowing conversions. Is that having conversions going both ways is just wrong. You need conversions to be a lattice. Then they're manageable and type safe if you do it right. Those are the major things I would do. I would probably also simplify the syntax. But people love the convoluted C-style syntax, so it would probably not be easy. That's all, but that's a minor thing. Yeah, that's. I think, as an example of the detail, I would not, when you write a template function using the abbreviated syntax, I mean void foo of sortable auto, that auto is redundant. Auto is the simplest concept. It's the one that says it must be a type. So that would go away, and all other details. There's then one thing over to do with R-value references that would have to be adjusted, but that's minor.
Okay, thank you.
And by the way, I should probably mention that I'm working on this idea of profiles, which are coding guidelines that are enforced, so that you can require them in the source code. And so you could, I would like to see an educational profile, for instance, which takes away a lot of the dark corners, mostly from C, and adds libraries to mean that you don't need them. And the type and resource safety profile is something I really want, but we will get some of it by 29, I think. It exists. Some of the core guidelines are enforced by Clang Tidy, Microsoft, static analyzers, and JetBrains stuff. So it's coming.
Okay. The next one is by Marco. Who is Marco? It's me. Okay. So what do you think of the future of programming with AI-assisted coding tools like Copilot and Claude and everything else? I think we discussed this yesterday.
Yeah,
but
this is a very common problem these days. I think mostly about applications that require high reliability, high performance, and a high degree of maintainability. And that is not what the ideal is for web coding, for instance. To which extent the Copilot helps, I don't know. But the fields I'm interested in, errors have major effects. And so you can't rely too much on AI, given the error rates we see today. People can generate code very fast, but then they really should review it carefully. People are not good at reviewing carefully. That's what we've got type systems for. And most people who could review a significant amount of generated code don't want to. I hear about senior developers retiring rather than being forced into a reviewer role instead of into a system designer role. So be careful. I hear some people claim that Copilot helps them a lot, and I see no reason to disbelieve that. But I think you actually need a fair amount of experience for using Copilot, and even more to use Claude. And the people who are most enthusiastic about it doesn't seem to be the kind of people that understand how to do those things in my domain. There are other domains and other applications where AI seems more appropriate. So I'm talking about applications that can ruin or maim people, and that you have to be extra careful. I mean, you saw me in almost paranoid mode in that previous talk. It's because of the area that I'm thinking about most.
Okay, this is not by me actually. So who is the guy who answered this? This is not by me, but I think it's interesting. Can you sing with a microphone? Since you mentioned before, I think, but this is probably a joke. Who is the guy who?
I probably could, but I won't.
That's a great answer. That's a good. Because you have to pay for this. You have to pay. Okay, so that's done. And okay, the next one is, what is the future of C++ with respect to newer and more popular languages like Rust?
I wonder why they claim Rust is more popular. Over the last 4 years, there's been over the last 4 years, there have become more new C++ programmers than there's been Rust programmers in total. And we're just not as noisy as the Rust people, and they have marketing dollars and things like what C++ has never had. But the best measurements I have seen recently says that the 3 fastest growing languages since COVID are JavaScript, Python, and C++ in that order. And then there was a few other languages, and then Rust just managed to get on the slide. Rust addresses a single problem and has some new language features which are very nice, but it's still more or less a special purpose language, I think. We'll see how it survives.
So the next one is, after C++ 29, with profiles and contracts in place, do you think the committee should consider standardizing or endorsing configurations maintained by major ecosystem organizations such as Boost?
I don't really know. The Boost and the C++ Alliance are mutating fast. So even if I had an opinion, I couldn't answer that question because I don't know exactly what it means. I think contracts are a good idea, badly executed. And so I am still worrying that I won't be able to recommend their use. And we didn't get profiles because people didn't think it was serious. It's a simple to address. And I think there's a very serious problem to address, a whole lot of problems really to do with complexity and safety of various sorts. And so I would like to see profiles in place, and I would like to see better analysis of contracts to see how they can be used. And I would like to see if they can be used, if they can be completed. Remember, they can't handle class hierarchies, and they can't handle pointers to functions. So if you like those and know that bugs comes out of those 2 areas, you probably should stay away from templates or from contracts. And furthermore, I don't understand all of those implementation defined features, how I can rely on contracts, unless I know all the implementation defined features in all of the environments my program should run in. And since I write foundational libraries a lot, that means I don't know the context of their use.
So I think you answered already to a part of this question. So, because it's about AI again, it's kind of trend nowadays, isn't it? Okay. So are you afraid of the future of human ability to think critically on software, but also in general life? For example, submitting code into production without understanding it, as new AI assisted is becoming popular and stronger. So what are your fears on AI?
I think it has been documented that AI interferes with learning. There's been some studies that says that if people hand in work with AI or use AI to quickly get an answer to problems, they don't actually learn as much and they don't remember as much. I think learning requires effort. Sometimes you have to bang your head against the wall and to get real learning. And so I think it will do damage to education of a large number of people. There are other research that I think are less well-founded, and there's just not enough of it, which says that really good students can use AI well, and poor students use it as a crutch. And so it'll actually separate people more than is done today. That would be very bad if it was true. I worry about AI-generated code in the domain I'm talking about. AI can generate good code for something that has been done 100 times and is done in a conventional way. A lot of the stuff I deal with has been done once or twice, usually by experts, quite often behind a paywall, so it's not used for training material, and where great harm can be done if a mistake is made. And on top of that, I'm trying to talk people into doing things in newer and better ways. And the training material doesn't have the newer and better ways. They get statistically drowned by doing it the good old way, like C arrays and pointers and that kind of stuff. So I'm in my domain, I am worried. I am not saying it is useless, but I'm saying that in what I'm most interested in, I have reason to worry. The AI is artificial, it's not intelligent.
Okay, we have a big fan, no. Okay, sorry. Okay, we have a big fan of Bell Labs legacy here. Is there any big fan? Okay, here it is. So do you have any memory or anecdote you're fond of that you are willing to share with us?
I guess I can say something. Bell Labs was a fantastic place. It was unique in the world, and there's nowhere like it today. So the Computer Science Research Center at some point had 60 members, out of which 4 was members of the National Academy of Engineering. The amount of talent and skill and knowledge were just stunning. And the doors were open. You could always go in and talk to somebody. If you needed an expert in anything to do with computing, you just went and talked to them. A lot of my work was done on other people's blackboards. I signed a Dragon book today. That's the book of how to write compilers by Alejo and friends. Alejo was my neighbor, so if I wanted to know something about compilers, I had the world expert right next to me. Dennis Ritchie is a really great guy, was at some point down the corridor from me till I fled down among the theoreticians because it was too noisy and busy up on the Unix floor. And I'm still talking to some of these people today, long after Bell Labs, as I knew it, died. It shouldn't have. It was a great waste of talent and skill when it closed down. Real anecdotes. I guess one of the good ones was that we had Arno Pensias as the boss of Bell Labs research. Actually, no, all of Bell Labs, I think. No, just research. He had a Nobel Prize, so he's a clever chap. And so Rob Pike and Ken Thompson set up an experiment to show some graphics and AI and stuff, and they to show how to do games and illustration of the games. And they took Pensias through corridors and talking to them and showed the stuff on the screen and such. And then in the end, they showed him that they had actually been filming him going through, so he ended up seeing his back of his own head. So, I mean, you could, people were reasonable. You could poke fun at them if you did it politely, and very collegial place. It really helped people. And when I came there, I looked at the names on the doors and thought, I'd better do something reasonably spectacular. Otherwise, I don't belong here. It's imposter syndrome was not uncommon.
Nice. Next one. So looking at what C++ has become now, and given how it evolved and still evolving, if you go back in time, would you design C++ any differently?
I think this offers the time machine question. And I sometimes set it as an exercise to my students with a picture of Doctor Who's TARDIS. Basically, the exercise is, okay, first you go back to 1974 and give Dennis some advice. And once you've done that, you go back to 82 or thereabouts and give me some advice. I could use it. The point is that most advice that comes from the students like that, and most advice we can give, failed because we don't have the technology to do it, even if you understood what it is. I started work on C++ on a machine where you had 128K of data memory. Dennis did the first C, then he had 48K of total memory. That limits what static analysis you can do, for instance, and how complex you can do things. I would like to improve the syntax. The syntax, sort of the inside-out syntax, came because Dennis didn't want to fit two syntax analyzers into his 48K of memory. And so he used the same grammar for expressions and declarations. And that's been a pain in the neck ever since. Though people love the complexity because then they're clever. They can write a function returning a pointer to function without using a type def, and they're proud of it. I don't think they should be proud of it. One thing that, curiously enough, I both would have understood if somebody had explained it to me and would have been able to implement while simplifying the language, is actually concepts. Templates without constraints gets much more complicated, harder to use, and actually harder to implement because every thing has to be checked all over the place. And so if you've got a time machine and go back to 87, 88, where I was working on templates, and explained to me about constant evaluated functions taking type arguments, you would have had a hard time convincing me. But I had the knowledge necessary to understand it if you explained it clearly enough. And it would have simplified the job of implementing templates. And I didn't myself implement the first templates, and I would have if I had known this, because it would have been easier and fitted my thinking better. So there's something that a time machine would have helped with.
So this one is from Rob. Is Rob in the room? No? Okay. Maybe he's online. What's the biggest mistake of C++ 26?
It's contracts. It's a good idea, badly executed, incomplete. They managed to make it both bloated and incomplete. It's that takes talent.
So next one is, which is the most important use of C++ you are aware of or proud of?
I mean, there's not just one, but most of them are sort of the scientific engineering things. When they found Higgs boson, I got an email saying thank you the next day. So I've done something for physics, even though I'm not a physicist, nowhere near. And so the stuff they do at CERN is absolutely great. I'll go there and give a talk in the summer. I mean, the stuff they do with space is interesting. The space communication stuff is C++. And the Mars rovers autonomous driving is C++. So the communication to them and when you let them off on their own is C++. Otherwise, most of the code is C and assembler, but the highest levels are C++. And then the Webb Space Telescope, a fantastic thing. I mean, think of having something running at L2. Wow. And I guess I could rattle on, but the point is, would you look under most rocks, you'll find some C++. So I wish I had gotten a label on that says C++ inside, but I didn't. And so your phone, your television, your car, your coffee machine, possibly. If you use one of those electronic things, I don't. Hope you don't, but certainly you can find it there. I found a bowling alley that was programmed in C++. It's you never know where you'll find it. I'm not proud of everything that's being done, but.
Okay, so next one is, do you think the evolution of languages like C++ will need to change now that most of the code will be read but not written by humans? Will clarity become more important than expressiveness? And can even envision a future where AI write code directly in some lower level intermediate representation?
First of all, I don't think most code will be written by AI, and therefore the premise is wrong. I think direct expression of ideas is good for humans and is good for AI. And yes, I see no reason why an AI couldn't write the intermediate representation. I designed one together with Gabby Dos Reis called IPR, and the binary version of that on Microsoft is called IFC, and is the backbone of a lot of the tool development. And I see no reason why you shouldn't skip the fairly convoluted syntax of C. On the other hand, you mustn't skip the type checking. I think types are absolutely essential. And I think some of these questions, like that one, assumes that you should think ambiguous and with very simplified type systems. That I don't like, and I think it's wrong for reliability, maintainability, and performance. But I see no reason why you should write characters on a screen for code.
So the next one is, what do you think about Linus Torvalds' arguments against C++? This is a tough one.
Well, no, it's an easy one. First of all, he writes C++ these days. Secondly, in 1996, when he made his big scree, I didn't use GCC C++ because I didn't think it was proper. And I wouldn't have written an operating system using that compiler. So if he had said the compiler is not up to it, my experiments with it has not worked out, I would have said, yeah, you're right, same as me. But then he says, it's an awful language and anybody who writes code in it is stupid. I don't think so. Part of the point is that C++ was not the cheapest language, not the easiest language, and we have no marketing department, and yet we have some number, more than 12 million users. They are not all stupid. So the other half of the scree is just completely wrong. They were not stupid then either. Some of them were us.
Another tough one. Will C++ ever get a more cohesive package management and build system like Golang does?
The newer languages have better tool environments than C++. Partly because we don't have an owner that will pay for it being built. Partly because when they build things, there will be many of them. We have package management systems like Conan and such, but they're not standard. Whether they can become standard, whether people can agree on it, people have tried to agree before, and they're competing vigorously. I mean, there's not more people using C++ package managers than are people using Go, but people don't take any notice. But yes, we should have better package managers, better build systems, and it would be nice if they were close to standard. By the way, there's an ISO rule that says that the language committee cannot design tools and standardize tools. We've been trying to get around that for years.
Okay. So the next one is, you often used to say, Evan I could design a prettier language. So has your mind changed after the latest developments in the C++ standard?
No, and a prettier language is even more needed than when I said that back in the early 80s. It's not a new thing. I used that phrase to try and explain to people that I was not trying to write something that looked good in an academic paper. I was trying to write something that was good for my users, and friends and colleagues to solve their problems. And that prevented me from doing prettier things like a syntax that was nicer, or an absence of conversions, which I come back to given today's talk. So it's more needed today. My approach to that is the profile stuff, where if you can add libraries for doing important things in a given area, and then subset away the troublesome spots. I mean, like, I want to get rid of pointers to pointers, for instance. You don't need them if you've got good containers. So you can get rid of a lot of the ugliness. So I think we'll see some of that in the next 3 years.
So what are the necessary steps to deploy new C++ versions?
You build it, and your supplier of compilers put it out together with a standard library the way they usually do it. Again, we don't have a standard. We have maybe 10 areas, 10 suppliers, and we can't do anything about that. It's not a monoculture, which is good in some sense, and there's a pain in the neck in others. But that's pretty fundamental. Yeah. If somebody breaks or defunds one of the major users, so there's the others. GCC was going stale, and then Clang came along. GCC is much better today. Microsoft was way behind. They are now, in terms of conformance, ahead. Competition is good, but also a pain when you want to deploy on a variety of things.
Okay, the next one is, so for Sergey, I don't know if Sergey or Sergey is here, okay. So most major game engines only use a subset of C++ up to 14, 17 to avoid latest. Do you think this is a sign that the language is not ergonomic enough for large-scale real-time systems, or is it just the cultural inertia of the game dev industry?
Two things. One is obviously cultural, and another thing is a matter of time. The latest surveys I have seen says that C++ 20 is now more common than C++ 17, even though some of the major implementers ship with 17 or even 14 as a default. Also, if you are writing code that other people depend on, that is safety critical, which is highly performance critical and such, you don't use the latest release, ever. You experiment with the latest release, and then when you are confident with it, you move your organization ahead. Moving your organization ahead is not simple. Like I worked for Morgan Stanley, and we couldn't use the latest because the operating system was Red Hat Release 7, and it couldn't run the latest because we needed the port from them. So there's always a lag, but I don't think there's anything fundamental with games or game developers that holds them back from 20. They can do good things with that. I think actually with 26, static reflection will get a lot of people on board, because a lot of the sort of macro-based CRUD that to get more information will go away. You can do without it, and compiling with modules will eventually get much faster. A lot of the early experiments was with the previous version of GCC, which was not as good as it should be. The new one is much better. I hear rumors that Clang is catching up too. Curiously enough, Microsoft was way ahead, but that's because of Gavidos Reyes, my old friend, who had a much better internal representation for modules, which was based on what we did in Texas, actually.
So what operating system do you run on your machine, on your laptop, on your PC?
My laptop, which is back in the office, back in the hotel, is a Windows box. But of course, I can run GCC and the Unix infrastructure there. And traditionally, I've had my production code on corporate servers and such. I am not doing anything currently at Microsoft where I need a bigger server. So I am not doing that, but I always used to run Windows, Linux emulations, and Windows boxes, and Linux boxes.
So so this is from Francesco. I don't know if Francesco is here. Okay. So in 2024, the American government has invited developers to move away from C++. So do you think, is it going to happen?
They have changed their mind and they're more specific now. They're saying certain things you shouldn't do, and most of those things you don't have to do in C++. That is the bad things. If you want to write C-style code, you get C-style bugs. They pointed out something like 70% of violations were things like buffer overflow. Closer analysis shows that was only of the ones that was in the language area. By far the major break-ins came through things like spear phishing or SQL injection. And Herb Sutter has a good talk coming out on YouTube soon about that. But anyway, out of those 70% that was language-based, something like 5% of those were C++ as opposed to C. And they were very busy mixing C and C++. So first of all, the old symbol condemnation of C++ has gone away to a more detailed analysis of what causes trouble and what doesn't. And apart from that, the data now shows that the data that was coming in showing C/C++ was causing security problems now shows that it was C to a very large extent, and the rest was C-style C++, which I'm working on a profile to simply eliminate. Also, we now have hardened libraries. You can get hardened libraries from Google, which I believe is Clang-based. You can get it from Apple. You can get it from Microsoft. So if you want range checking, you can do it. I have one problem. They're very keen on termination because of their application area. And if you are doing things where a single processor is, say, life critical, you can't just terminate if there's a violation. By the way, Linus has a wonderful rant against Rust because it terminates, and he points out that a kernel cannot terminate. It mustn't terminate ever. At least not immediately. You can sometimes do some clearing up and data hiding and then reinitialize or something. I've been doing that in other systems. So we need something better there. A friend of mine has a wonderful example, which probably is true, but I haven't verified it. His example is the oxygen controller for a scuba diving system. He claims there is one processor there. You can't terminate if you have a assertion violation or something like that, because that would be a fatal error. There are lots of systems that has limited resources. You don't have a Google server farm where you can terminate. I mean, after all that happens is that somebody doesn't get an ad, and you have 40,000 other processors. You just shift the load over there. It's a very, very different view of errors and error handling. And yeah.
So next one is from Maglio, if Maglio is here, or maybe he's online. Okay. So C++ has adapted to many changes in software development over the years. So in the age of AI-assisted programming, it's kind of a trend. What do you think will remain uniquely important about C++ and about the mindset of C++ programmers?
I think, as usual, direct representation of ideas in code, done in such a way that you can do new things and that you can do them efficiently. Well, reliability, maintainability, performance, but also expressiveness.
Well, that's probably something that
Not again. I don't do language comparisons because, well, partly because that takes a lot of work to do well, and partly because the fanatics wouldn't believe me anyway.
Oh, sorry. Maybe I skipped one. I'm sorry. Okay. What do you think that about some companies banning certain features of C++ from their code base? For instance, someone is against exception handling because they claim it makes code less efficient.
People who claim that exception handling makes code less efficient are just plain wrong. It doesn't. Not if you use them as exceptions. Very often, people who claim that use them as just an alternative return statement. That's not what they're for. They're for exceptional things, like you're doing an arrowing conversion. I've seen examples where exceptions simply speeded up code. You can have a couple of reasons. You can have exception handling crowding up utility on a very small memory, but there's a very good talk and some design by Khalil something or other, who you can find it on YouTube, that shows that even on very small systems, you can do exception handling so that it runs faster than good error code handling. If you use error code for really rare things, you tend to forget and get a lot of bloat for the if statements. So you can do better than that. It's a library, so if you're Clang-based, you can actually get the stuff. And by the way, that stuff was developed for microcode. Now there are reasons. If your code is a rat's nest of pointers and old-style, unprincipled resource management, exception handling is going to cause you trouble. And there are people who has had very bad resource management, having an exception eliminate a pointer that owned something, and then they blamed exception handling. Whereas since about 80, I don't know, 84 thereabouts, I've been saying you should never have a raw pointer being a resource handle, because then things go bad. It's not well organized. That's what constructors, destructors are there to handle in the form of resource handles, with the wonderful name of RAII. Horrible. Anyway, so no. So the assumption about performance is wrong, and the reason has to do with old code bases that are unstructured. If you have that kind of old code and you don't have the resources to modernize it, to get rid of the inevitable errors that are in it, you can't introduce exception handling either.
Okay, so the next one is, I think we have time for, I don't know if Tiberio is here for the timing, because we have some extra time, but okay, let's try to answer a few more questions. So this one is, what were the biggest challenges you faced while designing C++, and how did you overcome them?
I think the hardest thing was to convince people to use it. That's true for all languages. There's hundreds of languages invented every day, and hundreds of languages every year, and hundreds of languages die every year. And if you go back, we've been doing this for almost 70 years, which means that there's 10,000 languages that has come into use and gone out again. And that means that people are quite cynical about new languages. They've heard the advertising before. And I didn't have any advertising, no marketing organization. So all I could do was to show people what you could do, examples of what had been done, and then hope people would understand it and try it. So giving talks like this, I hope somebody here will be using concepts in interesting ways. That's all I know how to do. And then there's a paper about it. If you go to my homepage and go to the papers page, publication page, it's called papers. There's the paper called Concept-Based Generic Programming is the written version of what I was saying today, so you can look at it. But basically, I tried to travel around talking to people to see which of my ideas worked, which ideas people could understand, how would I explain it, listening to their problems to make sure that real problems were being solved, so that I wouldn't be in a bubble in Murray Hill with super clever people and experienced people. And so the hardest is actually, once you have solved the problem, how can you convince people to actually use it? That's much harder. People really seem to love to do what they used to do, even when it gives awful results.
Okay, this is about, so has someone who built a successful career in both Europe and the US, do you think the US is still the best place for a computer scientist and also C++ engineers today?
If I was just coming out of a European university today, I very much doubt I'd move to the States. It is partly socially, it's not as friendly and nice as it used to be, and partly there are more opportunities in Europe than there was when I was in that position. I mean, I got a job offer for writing commercial COBOL programs, and I got a job offer at Bell Labs. I mean, the distinction is just astronomical. There was nowhere like that in Europe at the time. Today there's more interesting places, many more. And the American suburbs are not quite as nice as they used to be.
The next one is, which is your most promising approach for writing provable memory safe C++?
The invalidation profile. So look up profiles. I have a paper at the last meeting for the standards committee. So if you go to WD21, just type in WD21, go to papers, look for this year and the previous year under my name, you'll find the explanation of how it can be done. And I'm not interested in just provable memory safety. I want complete type safety, except when you turn it off, and complete resource safety. I don't want to leak resources. So memory safety, as people go on about, is not enough.
So this one is very tough, I think. So did you enjoy Italy? And when will you join us again?
I do enjoy it. I set aside 2 weeks because I was going to give one talk, and I ended up giving 3 talks, 1 panel, and 2 AMAs. And I do see things. I went to Pisa in the rain. I've seen Florence a fair bit. Going to Venice tomorrow to see that, and then I'll head down to Siena and see the wine country. But when again, that I don't know. And as you know, it can take a lot of time. It's a big world.
Another reflection maybe in the standard.
We'll see. I hang out in Denmark in the summer. It's the weather is better there in the summer than it is here. I have been in Florence in the summer. It's
kind
not
of
my
hot,
number one choice for for July or August.
Yeah. So this is from Venice. Is Venice here around? No? Okay. So is it unbelievable that still in 2026 there is no support for extremely used things such as network in standard library? So we are integrating extremely nice new concepts these days, and we are still depending on external libraries.
I mean, if it had been up to me, we would have gotten the standard version of ASIO.io 10 years ago. And when I was advising a major financial organization on networking, we used ASIO. It's good enough and stable enough. So it's sort of a pseudo standard. And I'm saying, don't get fixated by the fact that it's not in the standard. Just use it. Go to the ASIO site and download it, or go to the Boost site and download and use it. It's industry strength. And yes, the committee should be able to get its act together, but last I checked, those 527 members, it's really hard to get things done there. Yeah, they wouldn't fit in this room, right?
The next one is from Vyacheslav, is here. Yeah, it's similar, it's related. It's about networking.
I answered that one. Yeah. Just use it.
Yeah.
I've used it in production. It's not hot air coming from here. It's experience.
So next one is, today's computer science students often start with Python and may never touch a compiled language. Is the pipeline of people who understand what happens below the abstraction layer shrinking? Should we worry?
Yes, we should worry. People who start with Python, by and large, have trouble when they hit algorithms and data structures and systems programming. and you need somebody to build efficient stuff underneath the Python if you're doing Python. And the energy consumption of Python programs are atrocious if you're using Python as opposed to just calling C++. So we should worry. And a lot of students are misled into thinking that all efficiency and maintainability and guarantees are somebody else's problem. Once you get a large Python program, you find maintainability is damaged. Now, the education talk I gave on Monday here, one of the things I was going on about was that I think we are making a big mistake of treating computer science or IT or computer literacy as one thing. I think that the education of people who want to build safety critical systems and the foundational systems should be taught computer science. And people who want to write web apps for small organizations, not Google, should be could very well be taught Java script or TypeScript or Python, but it's not the same. They are not the same people. They should not have the same curriculum. They should not have the same focus on exercises and evaluation. I think to solve this problem here, we have to bifurcate the computer education. And computer science, or what I would rather see computer engineering, but that means hardware these days. I would like to see well-trained computer scientists with an engineering bent being taught compiled languages, systems, built systems, maintainability, processes for guaranteeing performance and reliability. And that's where I'm aiming my work with C++. I don't feel like competing with Python. Gilder van Rossum aimed to serve everybody, and he succeeded. I aimed to serve well-trained engineers, and I succeeded. And there's the last measures hit those 16.5 million C++ programmers in the world. I'm not sure that works. I mean, I tend to say 12, but I used to say 7, and I was told and demonstrated I was wrong. So there's enough to sustain a community.
Okay, I think we can take the last two. Okay, so the first one is about your C++ story. Which is the idea you are most proud of? Which has been your biggest fail, if any? Does the fail help you to step forward? Maybe you already answered to part of these, but if you want to add anything.
I think my best idea was very simply the first. I decided to build a distributed Unix. And I found that no language could do what I wanted. I needed a low-level language for dealing with hardware things like memory managers and process schedulers. And I needed a high-level things that allowed me to say this runs here, that runs here, and they communicate with this protocol. And there might not be shared memory. So having had that idea, I took the similar class concept and put it into C so that I could afford it for systems programming. And to handle resources, I introduced constructors and destructors. And if you looked at code in languages in those days, they couldn't do that. Some of them have one initialization function, but that was rare. Giving people a choice of multiple constructors were not done, and nobody had a destructor to clean up the mess afterwards and to do resource management. So I think that idea in around the first week of CU classes was the best idea, and it's still driving C++. It forces us to deal with hardware, it forces us to deal with abstraction, and it forces us to deal with affordability of these things. So everything else that came second was derivative of that fundamental idea. And languages, by and large, have decided to give up on the low-level stuff and outsource it to C++ or C. So if you can't do the complicated stuff, somebody has to do your dirty work. And it ends up being, well, my stuff and Dennis's.
Okay, and the last one. So you've been very vocal about the difference between writing modern C++ and C with classes. So why do you think so many universities and legacy code bases still struggle to teach and adopt modern C++ idioms?
Partly because they go the C first way and teach people the bad old ways first, and then they don't have enough time. Partly because a lot of departments are fashion driven, and C++ is not the latest fashionable language. And so the old professors want Fortran and C, and the new professors want the latest fashionable stuff with a lot of Greek letters usually. So C++ falls between two chairs. This is unfortunate.
So with this, I think we can give another big round of applause.
Thank you.
I think we are towards the end of this, so thanks again for attending. I'd like to maybe come up here, the staff, so Alessandro, Federico, Tiberio, Michele over there. So, and so thanks again to the universities, so University of Florence with the Professor Berretti there, so, and the University of Pisa with also Tiberio. You have a double role, let's say. Okay, so please give a big round of applause. And again, thanks to our special guest, Professor Bjarne Stroustrup. Another applause. So remember the recommendation, we have some time, but don't touch Professor Stroustrup. So, okay. So I hope you enjoyed this extraordinary morning. I think it was amazing to have all of you here. So thanks again for coming. Maybe see you at the C++ Day in October. By the way, see you next time. Thank you.